Hello everyone, welcome to the electromechanical devices course. In this video we're going to continue the chapter 4 that we started the previous two meetings. This is the third video to discuss the transients. And the transients, it means that we are interested in investigating the behavior of the electrical circuit, like through the current or the voltage, how it would change just beyond the instant of time that we just close the switch to allow for the current to flow through the electrical circuit. We discussed that we do have, if we consider the general circuit, that would include the three elements, the resistor, the capacitor, and inductor at once in one electrical circuit. We shall end up with a second order ODE if we are interested in solving this ODE for the current. But for the case that we were excluding one of these two elements, like excluding the inductor or the capacitor, we shall end up with a first order ODE. In the previous video, we discussed how we can solve first order ODE. This is mathematical things. But we already covered this part just to remind you with these mathematical concepts of solving first order ODEs, whatever homogeneous or non-homogeneous. Today in this video, I'm going to show you how we can solve second order ODEs, because these mathematical things, we need them in order to study or do analysis for electrical circuit that include the three elements, all of them together: resistor, inductor, and capacitor. So the focus here through this video is on how we can do analysis to these RLC electrical circuits that include the three elements together. And as we discussed before, if this is the circuit equation that we can drive, that we already derived for RLC circuit, that include the L, which is the equivalent inductance of all the inductors that would be exist in the electrical circuit, and R, this is the equivalent resistance, and C, this is the equivalent capacitance, in addition to I, which is the current. That this should be solved for the current. But here we do have the VS, which is the voltage source, which is already also AC voltage or time dependent voltage. Generally speaking, if the current is given, but the voltage is the unknown, this is going to give us first order ODE, and we have to solve it as we did the previous meeting. But here, our interest is just to solve this ODE in the second, in the current, and that's why we're going to deal with this one as a second order ODE. And as you can see, it is non-homogeneous because the right-hand side that does not include any i's is already exists. It has a value. It means that this is a non-homogeneous ODE. So generally, how we can solve a second order ODE? Any second order ODE, whatever, for electrical system, for a mechanical system, generally speaking, mathematically pure, a second order ODE can be generated in this following form, where this is the second order derivative of the unknown. Our unknown here is the current, plus 2 xi omega n. This is xi omega n, this time, like two parameters that we just introduced them, so we can solve the second order ODE. In addition, these two parameters, they do have some specific physical meaning that we are going to discuss as well through this video. In addition to the first derivative of this parameter or this unknown, which is the current, plus omega n square, which is this omega, which is very similar to this omega, but this is just omega, this is the square of this omega. I of t, which is just the current, the unknown, equals f of t, where f of t, this is a forcing term, which is the right hand side. So generally speaking, as I mentioned, any second order ODE can be written generally in this form, whatever this second order ODE is for a current or for an electrical circuit, for a mechanical system, for hydraulic system, whatever it is, generally we can end up with or write this second order ODE in a general form, as typically what we did for a first order ODE. We introduced tau, which was like a time constant at that time for the first order ODE. We do have here two new parameters, which are the xi omega n, and there is another omega n on this side. Make sense? So if we try to compare these two equations together, you're going to find a very interesting thing here, that the coefficient of this omega second derivative term is L, but here the coefficient of this term is simply 1. So to convert this general equation of the electrical circuit into the general form of the second order ODE, your objective is just to make this coefficient equals 1. How we can do it? Simply divide all the terms by L. You're going to end up automatically with this term by doing some match between these different terms of these two different equations, or the same equations but with two different forms. So if we divided this equation, let us work over the equation up there, this one, just move it down here. And let us divide this equation by the L. So this is going to give us the d square I of t by the t square. The second term includes r. So this is going to be r over L because we're already dividing by L. The di of t by dt. And the third term includes 1 over c. So we're going to divide by L as well. So this will include L in the denominator. And we'd have here the I of t equal the force, which should be the dv. The first term is already y over L, and there is here dvs by dt on the right hand side, and this tv, it should be function of t, as we mentioned. Make sense? So we're gonna end up with this equation. If you try to compare these two equations together and try to come up with a specific value of omega n that we just arbitrarily assume this value, and the same thing for xi. So the first value that we can find directly is omega n squared. If you compare, this is I, so this term, it should be omega n squared. If you just compare, this is simply omega n squared, right? And this term r over L, it should give us the 2xi omega n. Make sense? This two, there is all the time exists, because this is, like, as I mentioned, this is a general expression for a second order ODE that would be used for representing any system, whatever electrical system, like this electrical circuit that we're already considering, or a mechanical system even. So simply we're gonna conclude that omega n squared, it should equal to the 1 over CL. From this we can end up that omega n itself, it should be the square root of 1 over CL. Make sense? What else? How about the 2xi omega n? If you try to compare the other two terms, and we're gonna talk about the units later, but for now this is the first term. The second term here, which is 2xi omega n, 2xi omega n, it should equal to the r over L, right? So if I ask you how much is xi, because we already found a value for omega n, right? So simply we can write like 2xi omega n, which is the square root of 1 over CL, equals r over L. Make sense? Then what? If you just did cross multiplication or solve this equation for xi, we shall end up with a specific value for xi, which it should be in this form. So xi will be obtained in terms of r, L, and c as r over 2 times the square root of c over L. If you just did some manipulation to this equation, we're gonna end up with a value for the xi and omega n in terms of the CL, R, and R of the electrical circuit. So simply, if you already given an electrical circuit with a specific resistance, capacitance, and inductor, you're gonna plug this data to end up automatically with omega n, xi, and xi of this electrical circuit. How about the f of t? We already have here another term, which is the f of t. This forcing term, it should be just collect all the right hand side term, which it should be simply the first derivative of the voltage divided by L, which is the inductance of the inductor, right? So simply we're gonna conclude that the f of t, the forcing term, is gonna be the 1 over L times dvs of t by dt, and this is gonna give us the forcing term. Make sense? Let us talk here about the units very quick and the physical meanings of these different terms. So simply, just to understand these different terms, this term, it is commonly known as natural frequency or just frequency. This is the natural frequency of that describe this natural frequency. Basically, it has a unit of radian per second, right? And because, as you know, the frequency generally it would be in hertz, which is just radian, or which is just like cycle per second, or radian per second if we are talking about angular natural frequency. If you remember the things when you studied the waves chapter in the physics class. But we're gonna go over this natural frequency and we're gonna explain its physical meaning. This one is known as a damping factor. This is commonly known as the damping factor of damping coefficient. All right, so this is the damping factor. And it is dimensionless. Dimensionless, it means that it shouldn't have any unit. And this one is the forcing term. This is the forcing term, or simply the force, like you consider a force. Force, generally speaking, it would be mechanical force, electrical force, it would be any type of a magnetic force, it is just a force, thermal force, it is a force. So force, it means that anything that do excitation to the system that we're already considering. This system here is just electrical circuit. Make sense? So what does it mean, all of these, or each one of these different terms, especially the natural frequency, the damping factor, and so on? Natural frequency, this is kind of speed, kind of velocity, how the current is going to change over time. The damping, how the current is going to decay or slow down over the time. So I'm going to give you a very typical example. So if we decided to plot a typical shape of the current function that we're supposed to end up once we solve this second order ODE, the current it should be obtained in this form. Like if we solve this equation, we're gonna end up with the current as I of t, and over the horizontal axis we're gonna end up, we're gonna have here the time, right? And if we try to solve or plot this function of the current, so initially we start with like kind of initial value for the current. Then the current is going to deviate, it's going to change over time like a wave, right? Like a wave in this way. And after a while it's going to slow down, keep slowing down till it will be reached to the steady state. If you remember, as we discussed the previous meetings, you could consider this is like another reference. And we can split this figure into two regions, as we discussed. A region that already, this is the steady state region of the curve, and this is the transient state, transient state of the curve, or the current, because our main concern here is the current. So as you can see, the current takes a wavy behavior, a wavy change over time, that it increases, it has a specific initial value. So let us give a name to this initial value, like I0, for example. This is the initial value of the current. So initially the current already given an initial value, then this current is going to increase with time. Then after a while is going to decrease again, then increase, decrease, increase, decrease, and so on. But the shift between increase and decrease is decaying, is already decreasing. So if we plot if we try to collect all of these tangencies, all of the tangent of these steps of these waves, you're gonna find that these steps already decreasing. This height is commonly known as the amplitude. This is the amplitude of this wave. This is the amplitude of another wave. This is like the first cycle, the first wave. This is the second wave. This is the amplitude of the third wave. So as you can see, the amplitudes of these waves already decaying, already decreasing. So decreasing, it means that we do have slowed down, kind of, or a change in this shape of the wave, generally speaking. The factor that describe how these waves are decaying, this is the damping factor, which is the xi. But how these waves already changing over time, this is already related to the natural frequency. So to understand more the natural frequency, for example, if we do have a current, I'm gonna just to explain to you, to understand the current, let us consider these two curves of the current. We probably, for some electrical circuit, we would end up with a current function that it will be described like this one. Or we may end up with a current function that just described with a wave like this one. So what is the difference here? The difference basically that I'm interested to show here, forget about the difference in the shape of the wave, but I'm talking about the length of each wave. This is the length, the wavelength, where we start from a point and move all the way, then you drop down again to a very similar point next to the next, in the next wave, the second wave. So if this is one wave, this is the length, let us give it a name like lambda. This is the wavelength or the length of this first wave. And this is the length of the second wave, which should be the same length, by the way. But anyway, this is the wavelength. But if we compare here, the length of this wave, it is too big, right? So what does it mean? Which one of these two waves do you think that is going to change faster than the other one? Which one is going to change over time very quick? This one on the left. Why? This means that this one, it has a natural frequency. This natural frequency here is bigger than the natural frequency here. Then omega n here is slower or smaller or of lower value. Okay, so what does it mean? It means that this wave is going to change over the time very quick. Like you would have something that vibrates very fast. So omega n, you could consider this is like the speed of the vibration, the speed of changing the current over the time. How fast this current is going to repeat this wave function over time. If this wavelength of this wave function it is too big, it means that this wave is going to change slowly, very slow over the time. So it means that the natural frequency of this wave it is too small in comparison to the natural frequency of this wave. It means that if this indicates that this natural frequency it should be very small in comparison to the other natural frequency of the other wave. So this is the physical meaning simply of the natural frequency. It describes the speed of change of a wave over time. This wave, if it represents a current, so we're going to say that this is the natural frequency of changing the current over time. If this wave they represent something else, so this is the speed of changing this something else over time. Okay? If it is high, it means that it's going to change over time very quick. If it is low or low, it means that it changes its shape or the wave function changes over time very slow. Make sense? How about the damping factor as we mentioned? If we do have there are two possibilities here. So let us also plot two other curves for the current, I of t. And this is the first curve. And let us consider another curve here. I of t. And let us assume that we do have this wave that already start initially, assume that the initial current was 0. So they start with this amplitude, then it's going down and then increase again and going down and increase again and going down. So as you can see, there is no changes in the amplitudes. The amplitude here is typically the same height, the same amplitude. We said that this is the amplitude, but the horizontal distance, this is the wavelength, right? So as you can see in this wave, the wavelength, which is lambda, it is still the same, typically the same value at the amplitude. Let us give this amplitude like uppercase I, for example. And this uppercase I, it is still the same height. This amplitude, it is still the same. And you should understand that within the same wave, we still have the same amplitude. All of these amplitudes are equivalent and it's gonna be the same all the time. Like no matter what, how long this wave is gonna work, all the time, this amplitude is constant. So we do have, in this case, we could consider that we do have constant amplitudes. And definitely the wavelength, it should be constant for all the electrical circuits. Let us consider another form of this electrical circuit, like this one, like a restart. Let us assume that it starts with a very sharp increase, very high amplitude. Then after a while, and this amplitude within the same wavelength. This is the first wavelength, it should have the same amplitude. Then in the second wave, the amplitudes became shorter or smaller. And in the third amplitude becomes farther shorter or smaller, and so on. Till it decays. So there is a kind of decay, decreasing in the amplitude, right? So we do have here a decreasing amplitude. The amplitude here, this is the amplitude one that is different definitely than the amplitude of the second wave or the second cycle. And this is the amplitude of the third cycle and the amplitude of the fourth. So as we move with time, we're gonna end up with a decrease in the amplitude, but still the wavelength is still the same, which is lambda. So we do have here, for this case, we do have a decreasing, we do have decreasing amplitude. For another electrical circuit, for example, or for another example, we may have an increasing amplitude. Make sense? So the rate by which these amplitudes are already decreasing, this depends on or can be measured using the Xi, which is the damping factor that we already mentioned here. So this Xi gives us an idea how fast these amplitudes are going to decrease, the rate of the decrease, or somehow they are related to the procedure or the way by which these amplitudes are already decreasing. So for example, for this case, there is no decrease or there is no change in the amplitude. Xi generally, it is not just decrease, it would be decrease or increase, as we mentioned. We mentioned that in some cases, you may have these amplitudes already increasing. So we do have three different scenarios, you could say. We do have one scenario that these amplitudes, they won't gonna change all the time. No matter what, how long this current is going to work, all the time the amplitude of the wave is fixed, it is constant. So for this case, there is no damping factor or there is no Xi. Xi in this case simply is going to be zero. But how about this case? Here we do have decaying, we do have decreasing thing, right? The amplitude is going to decrease. So this indicates that Xi is already less than 1. So if Xi, which is a factor, we said that a factor, this means that it is dimensionless. It has no unit, right? Just a factor. In case that this Xi is less than 1, it means that we're gonna have a decreasing trend in the amplitudes of these waves. The other option that in case that, like this case, how about if we do have I of t, the current, and this is the time, t. And in this case, we do have an increasing amplitude, like the amplitude is small and is going to increase up as we move with time. So we do have here an increasing rate of the amplitude. The amplitude I1 is less than I2, or I2 is bigger. I3 in the third wave became more bigger, where this in the same wave, you should understand that these should have the same amplitude, which is I1 here for the first wave, I2, and I3 is going to increase and so on. So we do have an increasing rate. So here we do have increasing amplitudes. So this indicates that this Xi, it should be bigger than 1. So it's just a factor that gives us, it is clear to us that this omega n, this Xi, these two parameters, they describe some specific physical phenomena or some specific things into this I of t. Simply, they describe how the current is going to change over time. Is it going to change at a high rate or at a slow rate? High rate, it means that omega n, it will be bigger or high value. Small values of omega n indicate that this current is going to change over time slowly, very slow rate. Xi, are we gonna have a decrease or increase or no changes in the amplitudes of this current over the time? The amplitude refers to the value of the current and how this value is going to the maximum value of the current and how this value is going to change over the time. So are the amplitudes of these waves of the current are going to change over time or not? If it is not, so there is no, in case that would have constant amplitude, it means that there is no damping factor. The damping factor is going to be zero. or this factor xi is going to be 0. In case that it is decreasing amplitude, xi should be less than 1. In case that we do have increasing amplitude, it means that the xi should be bigger than 1. Make sense? So these are the physical meanings of these two parameters. And here we knew how we can relate or end up or find the value of omega n, the xi, depending on R, L, and C. So if you're already given a specific electrical circuit with RLC circuit, simply you're gonna plug with the value of L and C and R. You can simply solve for or find omega n and omega and xi for any RLC circuit, and the forcing term definitely is gonna be depends on the time derivative of the voltage source with respect to the time. In case that would have DC voltage, so it means that the voltage, it will be constant. It means that this term definitely is gonna be 0. So we're gonna end up that f of t will be 0, and in this case we're gonna end up with a homogeneous second order ODE. So now, since we converted this ODE into an equivalent form, which is very general form that depend on xi omega n, simply the objective right now is just to solve this general equation, to know how we can solve this one. I won't gonna go deeply through the mathematics of solving second order ODE, but I'm gonna just give you a general outline how we can find the general solution of a second order ODE depending on omega n xi, that these general parameters that would be used for describing the second order ODE or a second order system, whatever this system is, an electrical system like these electrical elements, or it would be mechanical or any other system. Make sense? All right, so now let us see how we can solve this second order ODE that we generally said that any second order ODE for the current, it can be written in this form, like dt square plus 2 xi omega n and di of t by dt, which these terms shall be related to the R, L, and C of the given electrical circuit, and this is the forcing term that should be related to the given source. This is the second order ODE, and we would like to solve it. So typically, as you can see, this is non-homogeneous ODE. Why? Because the right hand side, it has a value. So generally, a general solution of this equation for the current I of t, the current, it will be the general solution. It will have homogeneous part plus a particular part, right? Like homogeneous solution and particular solution of this equation, as we did typically, as we did for the first order ODE. Make sense? And to find the homogeneous solution, and this is the first part, is just to work over the homogeneous solution of this ODE. And we said that this homogeneous solution, this what explains the transient behavior of this material, the transient state of the material, but the particular solution or the steady state solution, this what describes the steady state behavior of the material. So the homogeneous solution can be simply obtained by plugging I as IH into all of this equation and canceling the right hand side, just putting the right hand side equals 0. So this is going to give us this second order ODE, d square I of t by dt square equal plus the 2 xi omega n I of t, di by dt, di of t by dt, but you should understand that we're gonna plug here the subscript h plus the omega n square I h of t equals 0. So solving this second order ODE for the IH, this is gonna give us the first part of the general solution of the current, for the current. So to solve this one, we have to assume a trial function. This trial function, I won't gonna go deeply through the mathematical things because probably it's gonna take time, but I'm gonna give you the idea very quick. Usually to solve this second order ODE, we start with a trial function for the I homogeneous. A common trial function is the I of IH of t, it's gonna be like K, E, S, T, where S is just constant, K is another constant, and T, this is the time, E, this is the exponential function of S times T. Then if you plug this data into this equation, we have the second time derivative of the current IH, which is this function with respect to the time. So this is going to give us the S squared times K, right? Which is just a constant here. So simply substituting this function, then substitute into equation 1. Let us give a name to this equation as equation 1. So if we substitute it here, we're gonna end up with this expression. Like this second time derivative is gonna give us K S squared. The derivative, this K is constant. The second derivative of E is gonna give us S squared E S T. This is exponential function, right? And this plus the 2xi omega n is just constant. Di by dt, which is the first derivative of this function, gonna give us k s e s power t or e power to the st plus the omega n square, the I, which is just k e s t equals 0. As you can see that this exponential term can be cancelled with this exponential term, can be cancelled here. The k also they can be cancelled. Why? Because the right hand side is already 0. So we're gonna end up with s squared plus 2xi omega n s plus omega n squared equals 0. This equation in the mathematical things is known as the characteristic equation, or in the vibration course when you study is commonly known as the characteristic equation. Even for this electrical circuit, it is commonly known as the characteristic equation that describes some characteristic properties of this electrical circuit, the RLC circuit, depending on omega n and xi. So if we decided to solve this polynomial, this is like polynomial function, to solve this function, we're gonna end up with two roots for this s. This is the quadratic formula. So these two roots simply they're gonna be obtained as negative xi omega n plus or minus the I omega d. All right. I won't gonna go deeply through how this omega d or this I, which is this imaginary term, has been obtained. But anyway, these are the roots of this characteristic equation. As I mentioned, I don't want to go deeply through the lots of mathematics here because our main concern is the electrical things. But here we do have a new term that has been shown here, which is, I'm sorry, you're gonna be confused. So let us define this thing as J. This is not I the current, because we're reducing I, and omega d. This J here, this is the imaginary parameter, which is J equals the square root of -1. This is the imaginary parameter here. So we do have new term that already shown here, which is omega d. This omega d equals omega n square root of 1 negative xi. You have to xi square. You have to understand or just memorize this expression for omega d. This omega d is commonly known as the damping. This is the damping natural frequency of the system, natural frequency of the electrical circuit. So we discussed before the natural frequency, which is this omega n. So that's why n stands for natural frequency, or simply this is simply omega n, and this omega n is some of the properties of this electrical circuit that describe how this current is going to vary over time, or this wave how fast it's going to be repeated over time, as we mentioned. This omega d is an equivalent frequency of this system, but it do depend on the damping factor xi. So you could consider this omega n, which is this is the pure natural frequency of the system, assuming that this system has no damping. But basically there would be some damping in the system. There should be some decay in the amplitudes of the system, as we mentioned. It means that this decay or this damping in the frequencies or the amplitudes of the waves of the current, it would affect the speed by which these waves are going to change over time. And this is commonly known as the damping natural frequency, or just simply we can remove the word nature and say damping frequency. So the damping frequency, this is also another material property, but it do depend on both the natural frequency of the system, the pure natural frequency of the system, plus the damping coefficient that depends on how fast these amplitude are going to decay. So this is like a new natural frequency of the system, but that depend on the damping coefficient of the system. So these are the roots. If we plug this root into this assumed expression, this is the expression that we assume for the I homogeneous, we can find the solution. Because to find the solution, you should find K, which is just constant that can be obtained using some initial conditions. But the key issue here is how to find S. S, we're going to end up with these two roots. If we plug them here, we're going to end up with two terms for the IH, which is the homogeneous part. But this I, the homogeneous part, which represent the transient behavior of this electrical circuit, it do depend on the value of Xi. So depending on the value of Xi, we're gonna consider like 4 cases here. In the first case, in case 1, in case that you don't have Xi is already 0. This system, in this case, the system or the electrical circuit is gonna be considered as undamped system. Or in other words, the current is going to change over time undamped. What does it mean undamped? It means that the amplitude of the current wave will be constant all the time, as one of the cases that we explained up there. So this is the current I of t, the current homogeneous. We are talking about the homogeneous part. This homogeneous part will start either from 0 or any high specific value at time equals 0, but the key idea that the amplitude will remain constant. There is no change in the amplitude. All the time the amplitude is the same. The amplitude, which is I uppercase, this is the amplitude I uppercase, is constant. So the constant amplitude, we're gonna have here constant amplitudes. For this case, we mentioned update that Xi is already 0. So in case that we do have Xi equals 0, and we plug into this expression. So Xi equals 0, it means that omega d will equal to omega n, right? Which is the natural frequency. And we're gonna have this term will be 0 because omega 0 is already 0. So S12 will be just J, which is the square root of -1 omega n. So we're gonna end up that S12 will be just J omega n, right? If we plug these roots into this equation of the IH that we already got here, we're gonna end up with IH, which is the homogeneous solution of T, equals A, which is just constant cosine omega nt, and doing after some manipulations, plus B sine omega nt. You have to memorize this expression or this equation. This is the general solution for the electrical circuit for RLC circuits. This is the general solution for RC circuits. In terms of A and B, these are two constants. These are two constants to be determined using the initial conditions. But basically, since these are two constants, we need two initial conditions. We need two initial conditions. Why? Because we do have two constants. In the first order ODE, we had only one constant, so that's why we asked about only one initial condition. But since we do have two initial conditions here, or constants, we have to ask for two initial conditions so we can find A and B. What is omega n? This is the natural frequency that, as we defined it up there in terms of R, C, and L, we already defined omega n here. Omega n equals the square root of 1 over CL. So in case that you have C value, L value, you're gonna plug it here. Then in case that you have Xi equals 0 for some reason, if in case that you have R equals 0 or C equals 0, this term will be 0. So automatically, if you plug it here, we're gonna end up with this into this equation. In case that Xi equals 0, so we're gonna end up with this the homogeneous part or the transient part or the transient behavior of the current, it will be represented or described using this equation. This is the cosine function of omega t. This omega t, this is t the time. It means that this, all of this is the angle of the cosine, and this is omega t. T stands for the time. Okay, if we use this one, for example, and we plug this equation into MATLAB and we decided to draw this function, you're going to end up with a curve that the amplitude of this curve will not be changing over time at all. It means that this height I will be constant all the time. Make sense? This is the first scenario, the first case. In the second case, in case that we have xi is already changing between 0 and 1, or it has a value that is between 0 and 1. It is not 0, it is not 1, but it is between, like xi equals 0.2, 0.3, 0.8, 0.9, 0.999, and so on. So it means that it is not exactly 1, it is not exactly 0. Because if it is 0, this is the undamped case. For this case, the system, it is commonly known as underdamped system. It's going to be underdamped system. Underdamped system, what does it mean? It means that there should be a decrease in the amplitudes of the current. It means that if we decided to plot the IH, the homogeneous part of the solution of the current versus the time t, so the current will start with high amplitude. For example, even it can start from 0, but with very high amplitude in the first cycle, right? Then the amplitude is going to decrease in the second cycle and decrease more in the third cycle, and so on until it will decay. Almost there is no amplitude. So this is underdamped system. Here the amplitude I1 is bigger than I2, or I2 smaller than I1, I3 is bigger, is smaller than I2. It means that we do have a decrease, a decaying or decreasing amplitude. So we do have here decreasing amplitude. This indicates that this is commonly known as underdamped system. What does it mean, underdamping? It means that the system is working under the effect of the damping, and this would result in some decrease in the amplitude. And this is preferred in many of the mechanical systems, like the suspension system of your car. If you're really riding your car over a road, and for some reason there is a bump or there is something that is going to result in some vibration in the car, the suspension system includes some hydraulic system. This hydraulic system is working as damper to slow down the vibration. Without the damping system or this hydraulic system and the suspension system of the car, theoretically it should keep vibrating all the time. It's going to keep vibrating for a very long time. It means that the xi is 0. So having xi equals 0 in your car, it is not preferred. Why? Because xi is 0, there is no damping. This is undamped system for a car or undamped car. It is not preferred because, as I mentioned, if for some reason the car experiences some vibration, you're going to keep vibrating all the time, and this is not preferred. But for example, the underdamped system, for some reason, if there is a bump in the road or corrugated road, so you're going to vibrate for a while and then it's going to suddenly stop again. It will reach to the steady state very quick through some damping in the amplitude. That the amplitude, you're going to start with very high vibration, then this vibration is going to decrease. And this is preferred in some systems, in some application like the car, for example, as I mentioned, for the suspension system of the car, it is preferred all the time to work under this condition. The same thing for some electrical circuits. It is preferred to have this current decaying, and some other electrical circuit probably we may need to have this current increasing. And this is the third type that we are going to discuss, or the fourth one. So anyway, the second type that you'd have this xi is between this range. It means that this omega n, this omega d will be different because xi will have a value, and this omega n will be different than the omega d, or omega d different than omega n. And so it means that xi, you can find it as we express xi in terms of R, C, and L, and omega n you're going to find in terms of R, C, and L. Then you're going to plug them here to end up with omega d. And once the general roots of this case is going to be this one. So these roots, the roots of this equation will be S1 and 2 will be the negative xi omega n plus or minus the j omega d, where if you consider this is positive, this is going to give us the first root, negative, this is going to give us the second root. Then if we plug these roots into the IH equation, the exponential trial function that we assumed up there, which is this one, if we plug these two roots here, we're going to end up with the IH in this form that depend on two terms. So IH, which is the homogeneous part of the current, will be e to the power of negative xi omega nt, it is a function of t, times the a, which is another constant, the cosine omega dt, plus b, which is also a constant, sine omega dt. So this is going to give us the expression in case that xi is already between 0 and 1, where a and b both are two constants. These are constants that shall be obtained from the initial conditions. And again, we require or we need two initial conditions, typically the same like these two constants. Make sense? So this is the equation in case that xi equals 0. In case that xi is already within 0 and 1, this is the current, the homogeneous part of the current. This is its general solution. It is interesting to observe that we can drive this equation for the case that xi equals 0 directly from this equation. If you plug xi equals 0 into this one, so exponential of 0 gives 1, because anything power to 0 is just 1, so this term will be 1. A cosine omega d, we said that in case that where omega d, which is this one, in case that omega d or xi equals 0, this is going to give us omega d equals omega n. So intuitively, this is going to give us omega n and omega n a b, and which should be this same expression, right? So it means that if you plug xi equals 0 into this expression, you're gonna, or this equation, you're gonna end up with the IH for the case of undampened system. This is the second case. The third case, that we may have xi itself equals 1. For the third case, case 3, how about if we do have xi equals 1? So we consider the case that we do have xi equals 0, xi equals between 0 and 1, and now let us consider the case that you have xi equals 1. This is known as the critical damping system. This is the critical case. Okay, this is commonly known as the critical damping system. For the case that xi equals 1, omega d is gonna be 0, right? But because this is 1, this is gonna give us 0. Omega d equals 0. So what does it mean? It means that there is no frequency under the damping conditions, but there is omega n. Omega n will have a value. Omega n will be with a value, but omega d will be 0. So what does it mean omega d will be 0? It means there is no wave thing. There is no frequency. There is no change in the wave, okay, over time. There is no wavy behavior of the current. So for this case, for the critical damping, you're gonna find this system or the current IH of t changes in this way. Like this is the time t, and simply you're gonna find it. We start, for example, with some initial value, then it's going to decay over time, or it would jump up or increase somehow, then it's going to decay till at a specific, and it will reach to the steady state. It means there is no wavy behavior, right? This system, if the amplitude is decreasing, this is under damping. Here, the amplitude, there is no wave behavior of the current. The current will increase, then decrease, and it won't gonna move to the negative, as we used to have for the previous cases. This is the critical damping case. This is in case that we do have the xi equals 1. A typical example of this case of the xi one is the door. There are lots of doors that include hydraulic system, like you do have probably at home or even in the school. There are so many doors that you're gonna find that this is the edge, this is the joint of the door, and this is the door itself. Okay? And assume that these are the different joints of the door. And in some doors, we may have some hydraulic system here, like hydraulic piston, right? So if you try to open this door, you open the door, then you leave it, it will be just closed. It won't gonna swing both sides. But if it's going to swing, it means that this door has omega D. But this door, many of the glass doors, or even many of the doors that we are using in the institutions at home or whatever, if you try to close the door, open the door and just leave it, it will be automatically closed through the hydraulic system, and it will just close. It won't gonna swing to the opposite direction, right? This is a typical example of a mechanical system with xi equals 1. But there are some other types of doors that it would swing in both sides, forward and backward, like it keeps swinging in this way, right? And most of these doors, these are the short doors that made of wood, that would be used for the restrooms or whatever, right? So you're gonna find that this door is gonna keep swinging right and left, right and left, right and left for a while. It means that this door, it has omega n and omega d, right? But definitely in case that xi equals 1, this type of door, it has omega n will be with a value, but omega d equals 0. This is the critical damping system, a typical example of this one. So in some cases, we probably may experience an electrical circuit with this such behavior, that xi equals 1. So for this case, the current IH of t will be A plus B times t times the E negative omega nt, while the roots S1 and 2 will be just negative omega n, because the omega d term will be 0. The roots S1 and 2, omega d will be 0 when xi equals 1, and xi is already 1, so this is going to give us negative omega, and the two roots will be equivalent, will be equal. H1 will be equal to the negative omega. If we plug these roots into the trial function, we're going to end up with this expression for the current for the case that we do have xi is equals 1. The fourth case, how about if we do have xi is bigger than 1? This is commonly known as over damped system, and this is not preferred in many applications, especially mechanical application. Over damped, in this case, you're gonna find that omega d will be imaginary value, with imaginary value. Why? Because xi, it became bigger than 1. So if you subtract here one negative any value, so we're gonna end up with imaginary value, because this is already included in the square root, so this is gonna give us negative j, right? So it means that omega d will be imaginary value, or it is not preferred to define even this omega d for this case. And for this case, you're going to end up with S1 and S2. Both are real values, because this is going to secrete some imaginary value here. So this imaginary term will be eliminated, will be removed. So we're going to end up with this S1 and 2. They are real values. These real values is going to give us the current. I won't gonna write the expression for this case, but the current will be obtained depending on the hyperbolic trigonometric function, like cosine, which is the cosine hyperbolic of the omega n, or the omega n times the square root of 1 of xi squared negative 1 times t, and the sine hyperbolic function. And this function usually they would reach up to infinity. It means that for this system, we're gonna have the current already changing over time with unexpected behavior, and that's why it is not preferred. Like it would start with a very small amplitude, but suddenly it is going to increase that much, tends to infinity very quick. It means that we do have the amplitude is gonna be increasing. This is commonly known as this is amplitude 1, this is amplitude 2, this is the amplitude number 3. So this is commonly known as the over damped system, that we do have here increasing amplitudes. Make sense? So this is increasing amplitude, and that's why it is not preferred, because it is unexpected behavior of the system. So these are 4 different cases. The most important case that we're gonna consider all the time in many of the cases is this one, this case, for the under damped condition. So that's why this expression is highly important to acknowledge or memorize this expression for the case that xi is already between 0 and 1. For the case that xi equals 0, simply if you plug xi equals 0 into this expression, you're going to end up with this solution for the homogeneous. So this is the thing that you need to memorize, and for the IH, which is the homogeneous part of the solution. So this is generally for the first part, the homogeneous solution, and we said that this homogeneous solution would represent or describe the transient behavior of the current within the transient region of the current function. Now let us move to the particular solution. The particular solution, it depends on the forcing term. So we have to incorporate or include the forcing term then, as we did before with the first order ODEs, right? So now let us move to the particular solution. So this is the second part, the particular solution. And this solution is going to give us the steady state. This is going to give us the steady state behavior, or we can give it a name as the steady state solution that describes the steady state behavior of this current within the steady state region. So to drive this steady state solution, we need a trial function as we did for the homogeneous solution. But in the homogeneous solution, we had only one trial function that is commonly used. But here, this trial function for the particular solution, it would depend on the forcing term, the specific shape of this right-hand side term, which is the f of t in this equation. Or we already, yeah. In this equation here, the f of t, where it is, yes, this one. This f of t, it would be with any form, whatever it is. It would be constant value, it would be time-dependent value, it would be sine of something t, it would be any function, whatever it is. So depending on the function of f of t, we can assume a trial function. So there are lots of things, basically. So we can give like a rough or estimation of, let us consider this table, like some of the common function that would be assumed as and their corresponding trial function. For example, in case that f of t, this is the f of t column, and this is going to be the I particular as a trial function. This is the trial function that we're going to assume for the particular solution. Right? So for example, in case that f of t is a function like f0 cosine omega t, like in case that the f of t, which depends on the vs, remember that it is 1 over t, this f of t, it is 1 over L dvs by dt. If we did this right-hand side, and for some reason this right-hand side of the second order ODE, it was represented as a constant value, which is the amplitude of the forcing term, cosine omega t, where this omega is commonly known as the forcing frequency. This is the forcing frequency. This forcing frequency, it is different than omega n and different than omega d. Omega n and omega d, these are properties that depend on the system. But these forcing frequencies, these are external frequencies. This is to show how this force is going to change or vary over time. So far we have discussed 3 different types of frequencies that you should distinguish between them. We'd have omega n, we'd have omega d, and we'd have omega. Omega n, omega d, these are properties that depend on the system itself. Omega n, this is the natural frequency. Omega d, this is the damping frequency that depend on omega n and xi, which is the damping factor. The damping factor xi, omega n, omega d, these are properties of the system that depend on R, L, and C only. But this omega in this equation depend on Vs, depend on the source, depend on the battery, the voltage source, how much it is and its function. This is omega, which is the frequency, the forcing frequency, okay? Or we may have, for example, the force, it would be given like in the form of a sine, like sine omega t, or it would be given in the form of exponential form like f0 e omega t, where omegas, all of these omegas are the forcing frequencies that depend on Vs, as I mentioned, for this application, for this RLC circuits. And the force it would be given, or the Vs, it would be given in the form of cosine or sine or exponential or any other form, whatever it is. So, but these are some of the common functions that would be considered for the for the voltage source, and hence for the forcing term. Their corresponding, for example, in case that the forcing term was given as cosine function, so the trial function that we can assume is K1 cosine omega t plus the K2 sine omega t. Omega t, it means that this angle, it should be the same. If this is omega t, so it should be omega t, the same angle, but you're gonna consider cosine and sine terms, two terms. The trial function, it will be assumed as two terms, and if you plug this one into this equation, into the original equation that already given to us, that we're already using for the I particular, we can drive and solve this ODE to drive the particular solution. In case that it is sine, we're gonna assume for the same function omega t plus the K2 sine omega t. So basically, for any forcing term that is given in trigonometric function cosine or sine, we usually assume these two terms as trial function. And in case that it is exponential term, so we're gonna assume Ke omega t. I mean that this trial function, generally speaking, this trial function, it depends on the forcing term, the function of the forcing term itself. Then once we drive these trial functions, or assume this trial function and plug them up into this equation, the original equation that include the forcing term, into this equation, then solving this equation, doing the derivative and these things, we're gonna end up with an expression for, or a certain equation that can be solved for in terms of the K, in terms of this K. So I won't gonna go through the mathematics and the substitution, but the key idea, that the thing that you should understand, that this trial function for the steady state solution, it depends on the forcing term itself, how it looks like, the function of the forcing term. So generally speaking, we can end up with the particular solution of the current, or the steady state solution of the current. It's gonna be constant I times something here of omega t negative psi. This is the general solution that you should acknowledge or memorize for the particular part of the current, or the steady state solution of the current. So what are these terms? I, this is the amplitude of the current. I, this is the amplitude of the current function. But which amplitude? This is, to be more accurate, this is the steady state amplitude, because we do have another amplitude up there. We said that the general solution of the current, it is composed of two things: homogeneous solution and particular solution. The homogeneous solution represents the transient behavior of the current, right? This transient behavior, which is this part, the homogeneous solution, when we drive this one, we do have different forms. So as you can see, for this form, for example, we do have amplitudes, but this amplitude is already decreasing. So we do have the amplitude 1, amplitude 2 for wave 2, for wave 3, and so on, for the first cycle, second cycle, and third cycle. So we do have, for each cycle, we do have a different amplitude. It means that this homogeneous solution, it has amplitude. There is amplitude, and this amplitude simply can be obtained at the square root of the a squared plus b squared. It is related to this a and b constants here, right? But even in addition to this amplitude that we already have in the homogeneous solution, in the particular solution or the steady state solution, we have another amplitude. But how we can distinguish between these two amplitudes? The previous amplitude is known as the homogeneous or the transient amplitude, but this amplitude here is commonly known as a steady state amplitude. So if it was required from us to find the steady state amplitude, so we have to find the value for this I, and I'm gonna let you know how much is this I. This I, we're gonna drive this amplitude into this form. It's gonna be F0. What is F0? This is the amplitude of the forcing term, the coefficient of the cosine or the coefficient of the sine in the right hand side of this equation, as I'm gonna show you through an example. This amplitude of the forcing term divided by the natural frequency square. What is the natural frequency? This was that we drive it as a square root of 1 over CL, that depend on the capacitance and inductance within the electrical circuit as we define it up there. Square root of 1 negative r squared plus 2r xi r squared. So what is xi? Xi that we already defined up there in terms of r, c, and l. What is r? This r is commonly known as the frequency ratio. This r equals this r. It is the frequency ratio, which is omega over omega n. What is omega? Again, this is the forcing frequency. So that's why, which is this frequency in the forcing term. So that's why it is highly important to distinguish between this omega and omega n and omega d. So if you divide omega over omega n, which is the natural frequency that you're going to calculate in terms of C and L, you're going to end up with R. Substitute R here, xi, omega n, f0, everything it should be there. If you direct substitute, you're going to end up with the steady state amplitude of this function. What is this omega? This omega is still the forcing frequency. This is the forcing frequency. This omega, it isn't the natural frequency nor the damping frequency. This is the forcing frequency. Make sense? If you remember in the homogeneous solution, we already got here two different frequencies. There is omega d, that this cosine and sine, they depend on omega d. This cosine and sine here depend on omega n. But down there, and here even the expression depend on omega n. But down there here, this term is the frequency, forcing frequency, that included in the right hand side of the equation. What is psi? T, it is the time. What is psi? This is known as the phase angle. This psi is a phase angle. Psi is known as the phase angle, and it is just angle, right? Where this phase angle psi, it can be calculated as the tan inverse, because it is angle of the 2 xi r divided by 1 negative r squared. What is r again? This is the frequency ratio. You're gonna plug it here in addition to xi, you're gonna end up with the psi, which is gonna give us the phase angle. If you calculated the phase angle and the steady state amplitude, you're gonna plug them here in addition to end up with the particular solution. But how about this dash part? Here in this dash part, we are including the same function that already given for the forcing term. If the force is given as something cosine omega t, so this term, it should be cosine. If it is sine, it should be sine. If it is exponential, it should be exponential. It means that it should be the same function as the force. So here you just gonna plug here, put or substitute or plug here the same function, the same force function. If it is cosine, it should be cosine. If it is sine, it should be sine. If it is exponential, it should be exponential. Typically the same function, plug it here. Like for example, if this is cosine omega t, so you should have here cosine omega t negative psi. This is the angle of this thing. If this is the exponential, so it should be the exponential of omega t negative psi, which it should be, this is gonna be the exponent of the exponential function. Make sense? Once we find the homogeneous solution as we described it up there, this is the steady state solution or the particular solution. If we added them together, we shall end up with the total the total current function. It should be the homogeneous part as we discussed for the different four cases plus the particular solution. So this is going to give us the total current function. Then if we decided to plot this function using MATLAB, for example, we're going to end up with a specific wave. And then we can study this graph to investigate how the natural frequency or the way by which this wave of the current or the way by which this current is already varying over time. Make sense? So this is generally speaking how we can find the second order solution in case that would have an electrical circuit with RLC elements. The RLC circuit, as we mentioned, it is described as second order ODE, and this is how we can solve this second order ODE. Make sense? So let us put a summary of all the things that we discussed through this video here. In case that you already given an electrical circuit with R, resistor, and inductor and capacitor, C, with a voltage source as Vs, and this Vs is a function of time, C, L, and R, this is the RLC circuit. We said that for any RLC circuit, the circuit equation will be with this form as dl d square I of t by dt square plus the R di of t by dt plus 1 over c I of t equals dvs of t by dt. This is the circuit equation for any RLC circuit, right? As we already defined it up there. Make sense? Then we said that this ODE or this equation is a second order ODE, and it should be treated as a second order ODE as long as we are interested in solving this equation for the current. But we have to convert it into an equivalent form, right? This equivalent form depends on omega n and xi terms. So this is like the second, generally speaking, the second order ODE, which it should be this one. It can be written into this form, like d square I of t by dt square plus 2xi omega n di of t by dt plus the omega n square I of t equals f of t, right? Where the omega n, we agreed that omega n equals the square root or 1 over the square root of c times L, and its unit should be radian per second. This is the natural frequency. Also, we got the xi, which is the damping factor. This damping factor should be R over 2 times the square root of c over L, and it is dimensionless. So what does it mean? It means that in case that R and C and L already given within for a specific RLC circuit, you're gonna plug this data here to calculate omega n, omega and xi, and you should understand that this is gonna be the circuit equation in terms of this omega n and xi. How about the forcing term? The forcing term, f of t, is just gonna be a force. It should be the 1 over L times d square, times dvs of t by dt, and its unit is gonna be in Newton, because simply this is just a force. But generally speaking, this force, it would be given with any form depending on the vs itself. It would be given in the form of the F0. Then your objective is just to rewrite this one. You're gonna do the calculation depending on the given vs to convert this one into just constant times the cosine of something t. This something is gonna be the forcing frequency, or like F0 sine omega t, or even F0 e to the power of omega t. This is basically the three main, the common three function that would be used. So depending on the vs function that it would be given to us, we're gonna do this derivative, then we divide by L, and then your objective is just to compare the thing that you obtained here with any one of these functions to come up with the value of F0, how much it is, how much is omega, right? So this is the circuit equation for the second order ODE, or for the RL electrical circuit. Then solving for the current, it should be the total current. We said that it has homogeneous part, and the homogeneous part can be generally written as e to the power of xi omega n t times the a, which is just constant that depend on the initial condition, the cosine of omega dt, plus the b sine omega dt. This is the homogeneous solution, plus the particular solution that we agreed that it is I times something, and this function depend on which one of these forcing functions, times omega, which is the forcing frequency, not negative psi. As you can see, we have three omegas already shown into this general expression of the current for a second order or for RLC electrical circuit. We have natural frequency, which is this one, 1 over the square root of CL. We have the damping frequency. This damping frequency, omega d, equal the omega n times the square root of 1 negative xi square. where this one is only acceptable in case that we do have xi is between 0 and 1, or especially from 0 to 1. Even if it is 0, you can plug xi 0 here, you're going to end up with the corresponding value for xi equals 0 to the undamped system. But for the case that we do have underdamped system, this is going to be the equation or the general solution for the current, and this is what we are going to focus or consider through this course. This is for omega d, and in terms of omega n and xi, that you're going to find them here from these two equations. And so we do have omega n, we do have omega d, a and b just constant. This is I, which is the amplitude, and we said that this amplitude is going to be the f0. This is the magnitude of the forcing term. This divided by omega n square divided by the square root in the denominator 1 negative r square squared plus the 2xi r omega square or square. This is going to give us the amplitude. This amplitude is commonly known as the steady state amplitude. You have to recognize the names. So this is the steady state amplitude. This is the steady state amplitude. All right. In addition to this amplitude, we would have psi, which is the phase angle, which is tan inverse of the 2xi r divided by 1 negative r square. What is r again? R, we said that this r, I'm gonna write r here. R, it should be the omega divided by omega n. This is the frequency ratio. What is omega again? This is the forcing frequency, which is this omega, which is different definitely than omega n. If you calculate omega n, which it should be this omega n, and we do have omega, which is the forcing frequency, which is this term, you're gonna divide both them together to end up with r, then plug them here, you're gonna end up with the psi omega d and I, then substitute depending on which function. Your objective is just to plug the function here. You're gonna end up with the general solution of this current. You still need to apply the initial conditions to find A and B in case that there is initial conditions already given. So these constants, they do depend on the initial condition that shall be provided to us. Make sense? So this is generally how we can solve a second or a general solution. You have to acknowledge and memorize all of these equations so you can drive the solution for a second order ODE for an electrical circuit with RLC elements already located or used. Make sense? Now let us consider this example just to show you how we already gonna plug or substitute into these equations. Assume that we already given this electrical circuit, the RLC circuit, where it has capacitance and inductance in addition to resistance as already given up there, and this is negative and positive. This is the Vs function and this is R. R is already given by 10 ohms. And C, which is the capacitance of the capacitor, is given by 10 microfarad, and we do have the L, the inductance of the inductor is given by 5 micro or milli henries, as given up in this case. And the Vs function is already given as 20 sine 3000 t. This is the Vs function, which is V of t, right? And it is required to find the current. It is required to find the current I of t. Find the current I of t in case for the condition that I, for some initial condition like it is given as I of 0 equals 0. This is the initial condition. Anything that it will be provided at t equals 0, this refers to the initial condition, and also it is given like the di of 0 by dt equals 0. So these are the two initial conditions that already provided for the current. And again, it is required here, this is the requirement, it is required to find the current function. Make sense? So how we can solve this thing? Your objective is just to plug, to calculate. First step is just to calculate the system characteristics, which are the omega n, the omega n, the forcing term, in addition to the damping factor. So the first step, as I mentioned, is just step 1. Just find the circuit characteristics. What are these characteristic things? Your objective is just to calculate these 3 parameters, omega n and xi, in addition to the forcing term, the f of t. So the omega n, as we defined it up there, it should be the square root of 1 over CL, right? Equal the square root of 1 over, how much is C? C is already given to us for this electrical circuit. Okay, let me check the calculations here. Yes, C is already given by 10 microfarad, so it should be 10 times 10 negative 6. Why 10 negative 6? To convert from microfarad to farad, we need farad. Henries, it should be henries, but this is milli, so it should be multiplied times 10 negative 3, means that this value is 5 times 10 negative 3 henries. This value is 10 to the power times to the power of negative 6 farad, right? But this is just ohms, so there is no need for any unit conversion for this one, and this one is already given in volts. So this is gonna give us times L. L is already given up there by 5 times 10 negative to the power negative 3. If we did the calculations, we're gonna end up with 4,472 radian per second. This is gonna give us the natural frequency. Once we find the natural frequency, simply we can calculate xi. What is the equation for xi? Xi, as we mentioned, it should be R over 2, right? It should be R over 2 times the square root of, times, let me double check. Yeah, xi, we said that it is R over 2 times the square root of C over L. So it should be times the square root of C over L. So if we did the calculation, R is already given by 10 ohms, so it should be 10 divided by 2 times the square root of 10 times to the power 10 to the power negative 6, which is C, divided by L, which is 5 2 times 10 to the power negative 3. If we did the calculations, we're gonna end up with xi by 0.2236. And again, it is dimensionless. As you can see, this is less than 1. It means, what is the type of this system? It should be under damped system. So what does it mean? It means that once we find the current function, we are expecting, based on this value, we are expecting that the amplitude of the frequency of the current, it shall be decreasing over time. Why? Because xi is already less than 1, we do have under damped system. This indicates that the amplitude, it should be decreasing. The last term that we have to calculate is the forcing term. The forcing term, it should be 1 over L. It should be 1 over L. The time derivative of Vs of t by dt. This is how did we define the forcing term, right? L, we already have it. This is the function of Vs of t. So your objective is just to calculate equals 1 over L. L is already given by 5 times to the power negative 3 time the time derivative of Vs. The derivative of this one with respect to the time. The derivative of sine gives cosine. So this is going to give us the 20 times 3000 cosine 3000 t. Right? This is the derivative dv of this function up there. If we did the calculations, we shall end up with the forcing term. With the force, how much it is? Let me check the calculation. Yeah, we got it by the, okay, let me do the calculation myself. So it is 3000 times 20 divided by 5 times 10 to the power negative 3, right? Okay, 20 times 3000 times 5 times to the 10 to the, so this is gonna give us some big number here, which is the 12 times 10 negative 6, right? And positive, I'm sorry, 12 to the power 6, the cosine omega, which is 3000t, right? For if you compare this one, so as you can see, the forcing function, it depends on the cosine. So what does it mean? It means that directly this term will be f0 and this term will be omega. This is the forcing frequency, that we're gonna get here, which definitely should be different than the natural frequency. So from here, we're gonna conclude, or we're gonna end up that the F0 equals 12 times 10 to the power 6 Newton, or forget about, there is no need to bother yourself with the unit of this force, because it should be force anyway, but there is no need even to write the unit here. The omega, it is 3000, which shall be radian per second. This is the frequency, this is the forcing frequency, and this is the forcing amplitude. This is the force amplitude, but this one is the force frequency. This is the force frequency. Make sense? So this is the first step, just to find all of these characters. How much is omega n, how much is xi and f of t, in addition to f0 and omega. In case that xi is already less than 1, you're gonna directly calculate omega t. So omega t should be calculated in case that xi is less than 1, and this is the case. It should be omega n, the square root of 1 negative xi square. So if you plug omega n, which is 4472, and this xi, and calculate omega d, we shall end up with omega d. We're gonna find it a little bit smaller. It should be less than omega n, but the difference between omega d and omega n, it shouldn't be big difference. Just a few things. The omega n, it was 4472, but this one is 4358.8. The difference, it is not that big, so it means that we're already in a good shape as long as xi is less than 1. This is for the characteristic of the first step. The second step is just to write the circuit equation and then solve the equation. So the first step is just to find the circuit equation, or basically this circuit equation, it should be written the first one, but anyway, the circuit equation, it should be the L d square I of t, as we agreed, dt square, plus the R di of t by dt, plus the 1 over c, the I of t, equals the forcing term, right? This is the circuit, or equals the dvs of t by dt. This is the circuit equation. So your objective is just to solve, or basically the third step is just solve the ODE, the second order ODE. The solution of the second order ODE, you are not required to start it from scratch. Why? Your objective is just to plug the general solution. We drive the general solution of the current as a homogeneous part plus the steady state part. The homogeneous part, it is e to the power negative xi. It is xi omega n t times the cosine of omega dt plus b sine omega dt. This is the homogeneous part. You have to memorize these things, plus the amplitude times the function. What is the type of the function that we defined here for the force? We got it as cosine, so it should be I times the cosine of omega negative epsilon. Then your objective is just to substitute with the values to end up with the general solution for the current. So simply the xi, we already got it with the value, everything. We do have everything except 3 things, or 4 things, or 5 basically. We still need to calculate A, how much it is, B, because these are constants that depend on the initial condition. The time, this is because we need the current as a function of time, and we still need to calculate I and epsilon. So let us calculate I, the steady state amplitude. I is f0 divided by omega n square over the square root of 1 negative r square. All is squared plus 2 xi r square. You have to memorize these things. Equals. How much is f0? F0, we got it by the 12 times 10 to the power 6, and omega n, we got it by 4472. So plug these things here. So we do have the 12 times to the 6 to the power 10 to the power 6 divided by omega n, which is 4472 squared. This is on the numerator, on the top. Then the denominator, we do have the square root of 1 negative r, so we have to calculate r. How much is r? We're gonna calculate this one on the side here. R simply, r It is omega divided by omega n. How much is omega? It is 3000. This is this term. The omega, it should be the cosine in the forcing term. This is the omega term. It is already given by, we got it by 3000 divided by the omega n, which is the 4000. This is 4472. If we did the calculations, we shall end up with a specific value for R. So 3000 divided by 4472, this is going to give us 0.67. This value of R, it would be less than 1, it would be bigger than 1, it would be 0, it depends, right? It can attain any value. So anyway, it is, we already got it here by 0.67 squared, and all will be squared plus the xi, the 2 times xi that we got it 0.2236 times R, which we just got it by 0.67 all squared. If you did the calculations, we shall end up with the amplitude of this current, and this amplitude, it should be in terms of ampere because it is a current. So doing the calculation, we shall end up with a specific value for this amplitude. How about psi? Psi, it should be psi, the tan inverse of what? Of 2 xi r by 1 negative r square, right? Xi, we already got it by the 0.2236, and this one we got it by 0.67. If you substitute, also we shall end up with a specific value for this psi, that it should be in degrees. So it should be angle. This is angle in degrees, right? Because any trigonometric function after the calculation is going to give us a degree. This is for I and psi. So we got these two values here. Then your objective is just to substitute. So if we substitute with all of this data into this equation, we're going to end up with the current. So we can simply write the current function as E to the power of negative the xi, which is 0.2236 times 4472 times t, times A is a constant, cosine omega d, we got omega d by 4358.8 t, plus B, the sine of 4358.8 t. This is the homogeneous part, plus the amplitude that we shall find its value here. If we just calculate, let me check if I already did the calculation. No, I don't believe. Okay, so I didn't do the calculation for this current, but simply if you calculate here, you're going to end up with a specific value like this value here. This is the I, which is this term, cosine omega, which is 3000. So it should be the cosine of 3000 t, negative psi, which the same value you just gonna plug here. So this is gonna give us the current function. So we end up with the current as a function of t. Simply if we plot this one, we're gonna end up with like a wave behavior of the current. But there are still two things that we didn't find their values yet, which are these two constants. So now, and this is the last step, step 4. Is just to find the constants by applying the initial conditions. You're gonna do this step as long as there is I of 0 and di by dt of 0 already given. If these two initial conditions already given to us, this indicates that you are required to find the values of these two constants. But in case that these constants were not given, so in this case, you're just gonna finish. It means that there is no need for step 4. There is no need to calculate the step 4. And you're just gonna mention that this is a general solution of the current, and by applying the initial conditions, we can find the A and B functions, right? So to find these constants, we have to apply the initial conditions. Two initial conditions were provided to us. The I of 0 was given by 0, and the di of 0 was given also by 0. It is not necessary to be 0. It would be with any other value. It depends on the given function. How we can find this I? And as you can see, we have to find the derivative of the current with respect to the time. We have to find the derivative of the current with respect to the time. So your objective is just to differentiate this equation with respect to the time once, and you're gonna end up with a function. This function will include both A and B. Then you already have a function here for the current. So these two equations, you're gonna end up with two equations. If you plug T into these equations equals 0, you're gonna end up with two functions for A and B that should be solved for both A and B to find these two constants, because these, since they already two constants, we need two equations to be solved for these two constants. For example, if I plugged I into this equation equals T into this equation, the I equation equals 0, this is gonna give us, since this exponential T is 0, so this term will be 1, cosine 0 simply 1, so this is gonna give us A, sine 0 is 0, so this term will be cancelled, plus something cosine omega 300, 0 T will be 0 negative psi. So depending on the value of the psi, this is gonna give us the cosine, and the cosine, it gets rid of the negative sign, so the negative. So this is gonna give us I of 0 in this equation will be A plus the I, which is the amplitude, the steady-state amplitude, the cosine psi. This should be 0 according to this condition, because I of 0 should be 0. This is going to give us the first equation. From this equation, we can solve this equation simply for A. We can find A, how much it is. Moving this one to the right-hand side, this is going to give us negative I, the cosine psi, where psi and I, you got them as values. So it means that you already have a constant value for the constant A, or a specific value for constant A. Then if you did derivative to this equation, and then this derivative, you're going to differentiate this equation once. So this is the derivative of the multiplication of different functions, two functions. So the derivative is going to take time. So I'm going to skip this part for now, and I'm going to cover it in another lecture, okay, because of the time. But anyway, if we did derivative to this equation with respect to the time, we're going to end up with an expression. Then if you plug T equals 0, this is going to give us an equation. This equation, it will be in terms of A and B, both A and B. We got A, and you're going to solve the second equation for B. So we're going to end up with a specific value also for B. Then if you plugged A and B here, you're going to end up with the general solution of this current function. If you plot this function using MATLAB, for example, you probably would end up with a specific I of t. You're gonna end up with some, because we start from 0, you're gonna end up with some wave, depending on the different carrier. But we are expecting that the amplitude of this wave is going to decrease as we move with time. Make sense? So this is the basic idea, how we can solve a second order ODE, or how we can solve or do analysis for RLC circuit that is described by a second order ODE. Make sense? So that's it for this video and today's lecture. In the next meeting, I'm going to show you how we can use MATLAB for solving the first order ODE and the second order ODE for electrical circuit analysis. Also, I'm going to show you how we can use MATLAB for generating some plots and figures and see how these waves already changing over time that we already discussed here. All right. So that's it, and thank you, and see you in another video.